Okay. Here 4, the first derivative test for local extrema, okay? Applies to continuous functions. Critical points. Let's not forget, it's the slope. The slope is the derivative, right? Is 0 or undefined. So if we find a critical point, that's where the slope is equal to 0. We take the derivative, set it equal to 0. When we solve it, those are the critical points. Okay? Now, if your first derivative signs go from negative to positive, then there is a what? Think about it on that number line. If your derivative is negative, then it goes to positive, what happens at that point where it switches from negative to positive? It's a 0 slope, but it's a critical point, but what is at that critical point? What do we call it? It is a
horizontal.
Yes, the horizontal tangent. But get off the 0 for a second. And what do we actually call that? If the slope is going down and then it turns, it's going up. What is it? It's a minimum. That's what you're all right what you're saying. But those are all things that lead us to a local minimum, right? If the slope is going down and then it goes up, well, then there's a minimum point right there. Okay? And what about vice versa? The slope is going up and then it goes down. What point is there? That's a maximum point, okay? All right, now, these sound confusing, but when we start applying them, that's when you kind of get this stuff. If your derivative is less than 0 from the left endpoint, for any value of x bigger than a, the endpoint, then the endpoint is a maximum. Okay? What does that mean? Well, here's my endpoint. I'll try and do a little sketch for you right here. Here's my endpoint of the graph. Right there. Now, let's call that endpoint A. For all, here's my x-axis. For all x values bigger than A, aren't they on this side? Okay? This would be a maximum if your derivative is smaller, if your derivative is negative, less than 0 for all these points after A. You see what I'm saying? So, if I look at, and I will draw this again and we explain it again. What the heck wrong with me? This is point A. If all the points that are larger than A, our x values are larger than A on this side, right? Okay? If all their slopes are negative, see what I'm saying? This has to be a maximum. That's all it's saying. Okay? So if you're looking at point A and you look this way with your eyes and you go, oh no. And then you're noticing it's sloping down from A, then A is a maximum. Okay? It's confusing the way it words it. The picture's nice. The eyeballs are cool. The nose is pretty rancy. Alright? So, and vice versa, it's a minimum if it does the other thing. Okay? If your derivative is all positive from that point, okay, then you would have a minimum. Okay. And vice versa, if we're talking about that was an endpoint on the left, now if we have an endpoint on the right, it does the same thing. It's a minimum and maximum. It's the same rules that apply. Minimum. That's a new calculus term. Minimum. No, it's not. It's a new calculus term. It references the minimum. No, that's a typo. Okay? That's kind of typo. Okay. First derivative test for local extreme. The following test applies for continuous function. It means draw it without lifting off your pencil. Okay? At a critical point C, if f prime changes sign from negative, right? Changes signs from positive to negative, then we have a maximum. Okay? If f prime changes from positive to negative, we have a maximum. That's just a summarization of what we just said. Okay? Right. And that's what point 2 says. If it goes if it goes from negative to positive, then you have a minimum. Okay? You have a minimum. But be careful. Even though a situation like this, even though you have a minimum here, it's still the slope is undefined. Because it's a corner. Right? And if it does not change if it does not change, okay, meaning this is kind of positive, 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 the slope is positive, 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 positive. I mean, you don't have an extreme point there. You can't. If it doesn't go, if your slope doesn't change sign, you can't have a critical point, okay? Same thing here. This is constantly a downward slope, downward slope, downward slope, downward slope. You can't have it. And all this stuff is down here. This is a description of what I just drew with you with the eyes. There are your eyes. Hey! There's your nose, and you're looking down. Oh my God. That's maximum because the slope is all negative after that point. All right? True! The slope, it's pretty creative there. Anything for you. All right, and the same thing, it's going to be a minimum point if the slope after it is all positive. Okay? Concavity. This is the new stuff. We know when the first derivative is positive, it goes off. The first derivative is negative after that, and you know it's a max point. We know the midpoint, vice versa. This is the inflection points. The inflection points is to the second derivative, where the critical point is to the first derivative. Critical points happen in the first derivative, where the first derivative is equal to 0, right? So inflection points happen on the second derivative, where it is equal to 0.
Position, velocity, word.
Yes, kind of. Yes. So, before we get any further, when we're going to graph this, we got to take a look at the first derivative, see where it's equal to 0, and the signs in between those points. That tells us when the slope is positive or negative. With the second derivative, we're going to take the second derivative. That's also going to help us graph that same graph. That's going to show us where the inflection points are. And if the second derivative is negative, the function is concave down. That means a sad face. That means it arches down. Because not everything we draw is a straight line. That's crazy. You should draw a sad face to remind you. And if the second derivative is positive, the function is concave up. That's the smiley face. Okay? So we're going to start graphing some things that are, you're like, wow, I had no idea I can graph that without a calculator. You can, people, you can. All right? So, first derivative, when it's positive, the curve is rising. When the first derivative is negative, it's falling. So, up like this, down like this, okay? It's a possible location for a minimum or maximum when it's equal to 0. So there might be a horizontal slope there, which might possess an inner max, okay? The second derivative tells you whether if it's positive, it's concave up. The second derivative is negative, it's concave down. And the critical point for the first derivative is where it switches, right? That's the critical point. The second derivative, that's the difference where it might be a frowny face and then start to turn into a smiley face. That's the point of inflection, the second derivative. Just like the smiley face can change, that's the inflection points. Just like the slope can change, that's the critical points. They call them specific things. Where the slope changes, critical point. Where the concavity changes, that's the inflection point. Nothing too crazy. Okay, so now we're actually going to do this now. All right? Find any extreme values, points, and inflections, and then graph. Y equals x cubed minus 3x squared plus 4. All right. Now, I'm going to take the first derivative. Hey guys, what's the first derivative there? You can do that quickly now. 3x squared minus 6x. And if I set that equal to 0, I can find my critical points, right? So the first thing I'm going to do is what? I can take out a 3x. And what does that leave me with? X minus 2. So if I T-bone that, what are my two answers? X equals 2. What about this side? X equals 0. Right, because I said them both equal to 0. I'm supposed to say 3x equals 0. Well, I know x should be 0 there. And here I just flip it. right? X minus 2 equals 0. So those are my two critical points. So, and we've done this all before. Now we're actually just going to put it on the graph. That's the only new difference. And we're adding concavity. So, I know if at x equals 0 and x equals 2, those are my critical points with 0 slopes. I should call this y prime. I'm sorry. What if I put in the number 1? If I put the number 1 into my first derivative, is it positive or negative? It's negative. Because what is 3 times 1 squared? Well, 3 times 1 is 3. Minus 6 times 1 would be 6. 3 minus 6 would give me negative 3, wouldn't it? So it's negative here. What about if I put in the number 3? What is 3 squared? 3 times 9? Minus 6 times 3, which is 18. 27 minus 18? It's 9. It's positive 9. Now what about if I put in a negative 1? Will that change it? No, because negative 1 squared is still 1. So that's 3 times 1 is 3. Negative 6 times negative 1? Positive 6. So that would also be a 9. It's positive. So when it comes to this point here, it slopes up to 0. Then it slopes down to 2. And it slopes back up after 2. It flatlines at 0 and at 2. Because that's where it changes. Yes, this is negative. You see what I'm saying? It goes positive, negative, positive. Positive slope, negative slope, positive slope. Now at this point, I can actually find those coordinates. I give these coordinates. If x equals 0 and at x equals 2, how do I find the y's for those values? Plug it into the original. That's what will give me my y. Someone tell me, when I throw a 0 into my x here, what's my y value? 4. That's an easy one. So it's 0, 4. That's going to be, maybe that's going to be a max point, right? Looks like it's going to be a max point. Because it goes up, then it goes down. So I'm going to write max here. What if I throw in a 2? Obviously, that might be a midpoint. It's going to be lower. Is it 0? What is 2 cubed? 8. Okay? Minus, what's 3 times 2 squared? 4. Well, that's 12. 8 minus 12? Plus 4? So that is at 2 comma 0. And that's a midpoint. Okay? So you see how I did that? So on your notes, when you look back at this, you're going to say, how did he get the 4 for the 0? You're going to know that it goes in here. I'm assuming you do. That's why I'm not writing. Because we can do that math in our head. Okay? That's the first derivative. What about the second derivative? What is the derivative of the derivative here?
6x times 6.
Y double prime is 6x minus 6. So does that equal to 0? What is the value of x that makes it 0? It's 1. So now, our 0 is at the number 1. And we call that our inflection point. Not our critical point, it's inflection point now. So, what happens if I pick a number bigger than 1? What happens if I pick 2? Will that be positive or negative? It'll be positive. What happens if I pick the number 0? It's going to be negative. So remember, this is the second derivative, so it's not slope, it's concavity. Sad, because it's negative. Happy, because it's positive. And there's going to be an point of inflection where x is 1, but I need to find the y value of the coordinate. Which means I got to do what with that x value? Plug it into the original. 1 cubed is 1. Minus 3 times 1 is negative 3 plus 4. What is that? 2. So at the point 1 comma 2, that's our inflection point. All right? So let's start putting some of these points in the graph. Okay? We have a max point at 0, 4. So at 0, 1, 2, 3, 4. Max point right there. We have a midpoint at 2, 0. Right here. 2, 0. And then we have a point of inflection where? at 1, 2. At 1, 1, 2, right here. All right? Now, if I wanted to get, find the y-intercept, I can make my x is 0, it's 4. We just graph this at this point. All right? I know the slope should be, now pay attention here, don't write this down yet. The slope should be positive until it hits this point, right?
Yeah.
Here. And it's going to come negative down to where it hits this point, but it's going to come back up. That's according to the first derivative, right? At 0 and at 2, those are my min, max, and min. And I also know, based on my second derivative, that I'm going to have a sad face, yeah, I guess frowny, whatever I want to call it. I'm going to have a frowny face until I get to 1, because that's my point of inflection, right? So it's pretty much going to be a frowny face here, and it's going to start to be a smiley face right there, right at 1. So it's going to be curvy instead of straight lines. Yeah, so let's bring that sad face here, and here's a max point. It's going to kind of look like this. And then from here, it changes to a smiley face, like that. Now, I think I'm pre-calc to do this. Now, if you want to get specific, like, hey, well, how do you know it touches here, Visca? I don't. Let's say if I put a negative 2 in for an x, what would my y be? Let's do a negative 2. Negative 2, that'd be negative 8. All right? That minus 12 plus 4. So that'd be minus 20 plus 4, which would be minus 16. So at 2, this thing will be like way down here. So it would really drop faster. Okay? So, I mean, I would, if you want to get like a little bit more accurate, I would check maybe 1 point left of this and 1 point right of your farthest right point. Just to make sure that after it passes that point, it's going through the correct next point. You can get an idea. Like, what happens if my, what happens if my x is at 3? Well, that's going to be 27 minus 27 plus 4. It's going to be at 4, won't it? So at 3, which is 1, 2, 3, 4. See? So that should, when it comes down here, should be a little bit steep. Once you do that, you're good. So I would recommend you going 1 point further than your farthest right, and 1 point further than your farthest left. Okay? And if we want to check that, we can. Yes, we can. So here we go. Clear. Clear. What is the original formula? X cubed 3x squared plus 4? That's pretty good. There's nothing better in life than when you're right with things. It's pretty good. It's really accurate. It's crazy, right? Hey. Example 4 says, reading the graph of the derivative. Okay, the graph of the derivative of a function of f on the interval -4 to 4 is shown right down here. Okay? Answer the following questions about f, justifying each answer with information obtained from the graph of f prime. Okay? So, this is actually the derivative right here. This isn't the original function, it's the derivative. All right? And here's where we've got to be careful. Because we've got to think of that derivative. We've got to go backward to the original function. Then we can kind of go forward to go to the second derivative. So, on what intervals is f increasing? Right? If this is the derivative, we know that the original function is increasing when what? The derivative is? When the derivative is positive, which means it would be above 0, which means it would be above the x-axis, right? The derivative, this is the derivative, okay? The derivative is positive from here to here, and also from this point to this point. Positive and positive. So what intervals? Well, from -4 to 2, or excuse me, -4 to -2 it's increasing. And from -2 to 1, right? Yes.
Can she said that waited for the water is like
They should split them up because I think at 2 it's actually 0. Which means, and as I was writing this, I was thinking this might be, we don't want to include 2 because at 2, the slope would actually be horizontal, which is a 0 slope. Right? Now, here's where we've got to reverse the way we're thinking. On what intervals is the graph concave up? That means the second derivative has to be positive, right? If we have the first derivative here, we got to think of the second derivative. All right? So, and follow me here. Listen real carefully. The first derivative is the slope of the original, right? So the second derivative will be the slope of the first derivative. I will one more time. The first derivative, that represents the slope of the function, right? Derivative is slope. Well, what is the second derivative? Well, that's still a derivative, but it's the derivative of the first derivative. Do you see what I'm saying? So, if I have a function, the slope of this is f prime, the first derivative. You always take a derivative down to get the slope. So if I want the slope of f prime, I would go to, right? So the slope of f prime is going to tell us f double prime, second derivative. So when I look at this right here, again, this is the first derivative. I want to know where it's concave up. That's where the second derivative is positive. That means they want to know where the slope of the first derivative is positive. I'm not looking above the x-axis anymore. I'm looking at the slope of that. Where is the slope positive? From here? No. That's negative, right? Yeah, so let's say from -2 to 0, it looks like that's a positive slope. And where else? From maybe 3 to 4, that's positive slope. You see what I'm saying? So you got to be really careful. Sometimes you're thinking above the x-axis for positive. Sometimes you're thinking of slope. Just take a moment to really look at it, read the question, know which one you're looking for. So it's concave up from -2 to 0, and also from 3 to 4. All right? At which, let's see, let's look at D. At which coordinates does f have local extrema? Local extrema are at critical points, right? Is that first or second derivative? First derivative. So the critical points are when the first derivative is 0. This is the first derivative. What is it equal to 0? Yeah, -2, it's equal to 0. It's equal to 0 at 1, and actually at 4 again, right there. That's when the first derivative is 0. Okay, extrema means critical points. That means when f prime equals 0. That happens at, as you said, -2, 1, and 4. What are the x-coordinates of all the inflection points? Inflection points are second derivative, right? That's when f double prime equals 0. Isn't f double prime the slope of f prime? So when the slope is 0, at what points on this graph? 0, 3, at 0, at 3, and at -2. Okay? Yeah, the slope, this is f prime, right? The slope will be f double prime, wouldn't it? Which means the slope is 0 at this point. Okay, so that would be at x equals -2, 0, and it looks like about 3. One more, oh my goodness. Sketch a possible graph. All right? Sketch a possible graph. So, this is what we're going to do. says a possible graph because this might differ. The only real information you have are the slopes, whether it goes up and down the critical points. You don't have, how far up sometimes it goes or how far down. You only have the x value. We can't find the y value because you don't have the original function to put that in, do we? No. So let's do it this way. I know for a fact that what? It is increasing. I will go from 1, 2, 3. Here's -4. Here's 1, 2, 3, 4. Okay? It's increasing from -4 to -2. So I'm just going to do a little sketch down here. I know it's increasing from here to here, right? It is also increasing from -2 to 1, which is right here, which is the one. So it's going to continue to increase from here to here. Okay? When is it concave up? That's a smiley face, right? From -2 to 0. You kind of smile up from -2 to 0. Okay? Where else? From 3 to 4? This is 3 and 4. We're going to have a smiley face up here as well. Okay? Which coordinates have local extrema? So at -2, we're going to have a critical point here, CP at -2. At 1, and at 4. That means the slope is going to be 0 here. And last but not least, inflection points at -2. Okay, right. This means it's going from smiley to sad right here, isn't it? And it's still sloping downward. The sad face is going to slope downward like that. All right. At 0, this was smiley, and now it's going to be sad. And where else? At 3. So from here to here. It's going to go sad, boom, then switch from here to go back like that. Okay? So that's probably a good... It's sad, kind of flattens out, keeps on coming up. Comes up to 1 where there's critical points, and changes, and then kind of ends, boom, like that. It's not too bad. That's tough because you don't know. Okay, critical points at -2 where? Is it -2.5? Is it -2.2? You don't know. That's why possible graph. As long as you have something that kind of curves like that and has a slope the same spot, and your critical points at the same spot, your smileys and tags at the same spot. Let's go. Study motion along the line. F derivative. That gives me what? So x prime, which is velocity, which is what?
6t squared minus 22. That's j plus 52.
All right. I would probably put that in your calculator and see where it touches the x-axis to see what the critical point is, right? If we want to set that equal to 0, we could factor and solve. Or put it in your calculator. Someone want to do that? Put that in the calculator and tell me what you get? You guys. 1, y equals, what is it? 6x squared. What's next? Minus 28x? 6x squared minus 28x plus 22. Yeah, and left the 22 out. Sweetness. Two, graphic. There you go. Okay, what are those 2 points? I can calculate those using my 0 function. Enter. Enter. Someone write down 1. That's nice. That's crazy. I'm going to calculate my other 0. Enter. Enter. 3 point. Well, that's actually 3 2/3. So you do 3 2/3. So at 1 and 3 2/3, it is not moving at all. Remember, its velocity. What about if I pick the number 0? Will it be positive 42? All right. We'll look at the graph for this one. What happens if I pick any number bigger than 3 2/3? Well, isn't that above the x-axis? it's positive. In between, it's below the x-axis. So it's negative. So it will go, this means it's traveling right. It is traveling left. It stops at 1, goes back left, stops at 3 2/3, and goes back to the right. And what is acceleration? That's the derivative of velocity, which would be what? 12t minus 28. So that'd be 28 over 12. 28
14 over 6.
over 12.
7 over 3.
Which goes 24 and 4 12. So that's 2 and a third. That's 2 and a third, 7 thirds. So on here, if this is a 0 at 7 thirds, or 2 and a third, what happens if I put a number smaller, 0? It becomes negative. Bigger number is positive. This means what? Acceleration. It's going to be acting negatively based on its velocity. It's decelerating, right? Negative means here it is decelerating, and here it's accelerating.